Welcome to Learning Math. We're doing power series in calculus, and this is example 3. The examples must be done in order as they get increasingly complicated. So the instructions are find the interval of convergence for the power series summation n equals 1 to infinity x minus 3 to the n over n. So this question is the same as the questions that we had for example 1 and 2. And there we had find the values of x for which this power series converges. Here we just, and the answer was always an interval. Here we just saying find the interval of convergence. And we'll use the ratio test again. So solution. So this is actually a longer problem than the previous one. So let me see if I can conserve some space here and write small and fit it on a page. So by the ratio test, limit as n tends to infinity, an plus 1 over an is, and once again we put n plus 1 in place of n. So that's going to be x minus 3 to the n plus 1 over n plus 1. And then the denominator is just x minus 3 to the n over n. The absolute values. Might forget the absolute values, not a big deal. But it's there. It matters at the end. So then we'll use fraction arithmetic, a over b, all that over c over d. You flip the denominator, a over b times d over c, right? So we write this as limit as n tends to infinity x minus 3 to the n, x minus 3, all that over n plus 1, and then start over n in the numerator there, x minus 3 to the n. So cancel out what you can. And what we're left with is limit as n, sorry about that, limit as n tends to infinity n over n plus 1, x minus 3. So I can factor out the x minus 3. It's a constant with respect to n. So limit as n tends to infinity, n over n plus 1. And I hope that now a simple limit like that, it's very easily seen to be equal to 1. Maybe it's not so obvious, in which case you would take it out here and do it separately as part of your rough work. The strategy is divide numerator and denominator by the highest power of n, so that's n over n plus 1 over n, so you end up with limit as n tends to infinity, 1 over 1 plus 1 over n. This bit goes to 0, so you're left with 1. This is a standard limit problem from Calculus 1. And see, we forgot our absolute value signs. And because we forgot our absolute value signs, we put a bracket there, and that's not correct. So must remember those absolute value signs, I suppose. And it did not matter here. So this is equal to absolute value of x minus 3. Not just x minus 3, but absolute value of x minus 3. So by the ratio test, which we reviewed for the previous example, the series, the power series, converges for x minus 3 absolute value less than 1. And that by precalculus is minus 1 less than x minus 3 is less than 1. So you simplify this a bit, you add plus 3 to all sides. So you get 2 less than x less than 4. So what you have is this interval here, say 0, 1, 2, 3, 4. And the interval of convergence is 2 to 4. Now the ratio test is inconclusive at x equals 2 and x equals 4. So we have to do something else for them. So far, we know that it converges within 2, 4, but let's think about 2 and 4. So if x equals 2, then what we get in our power series when we put x equals 2 is this. And this is your standard alternating series. It was the first example we did in alternating series, and it converges by the alternating series test. And maybe we've forgotten what the alternating series is, so let's just quickly review that. So this is a long problem comparatively. So what does it say? Recall alternating series test. You can put AST. If AN is a sequence that is a decreasing sequence, like 1 over n, with AN greater than 0 and limit as n tends to infinity, that didn't look like limit, LIM, as n tends to infinity, AN equals 0, then the alternating series minus 1 to the n AN and n equals 1 to infinity minus 1 to the n plus 1 AN, both will converge. And this fit the profile of the alternating series test. It was actually the first example that we did in the alternating series. Example, summation n equals 1 to infinity minus 1 to the n 1 over n. What is it? It's minus 1 plus 1/2 minus 1/3 plus etc., right? So AN is 1 over n, very definitely a decreasing sequence. It meets the 3 conditions. AN is greater than 0, and limit as n tends to infinity. I'll write it here. AN is equal to 0. So by AST, summation minus 1 to the n, 1 over n converges. So in the previous series section, when we did alternating series test, this was like, a problem by itself. Now it's just a part of the other problem. Here I go, talking with my hands again, and nobody can see me. So it's just a part. It's just a part of the other problem when x is equal to 2. So, and similarly, when x is equal to 4, if x equals 4, what you get is a summation n equals 1 to infinity 4 minus 3 to the n over n. So this is summation 1 over n. This diverges by the p-series test. When we did the p-series test, this was one of the things that we did. Let me remind you of the p-series. If p greater than 1, then summation 1 over n to the p converges, and in fact it converges to 1 over 1 minus p. Sorry, I think that's 1 over p minus 1. And if 0 less than p less than or equal to 1, then summation n equals 1 to infinity 1 over n to the p diverges. So the answer here, I'll give you a moment to catch up and think about it. Ready? So summation n equals 1 to infinity x minus 3 to the n over n converges in closed brackets to open brackets 4, because it converges at 2 and diverges at 4, and radius of convergence r equals 1. Okay, so there you have it. This is a problem where c was non-zero. In the previous problem, c was 0. Here, c is equal to 3. So the power series is centered around 3. So limit as n tends to infinity, an plus 1 over an ends up being this. So by the ratio test, the power series converges for absolute value of x minus 3 less than 1, which ends up being this. And here is our picture. So if x equals 2, then you get an alternating series, which converges by the alternating series test. If x equals 4, you get a p-series, which diverges by the p-series test. And therefore, the final answer is the series converges in closed interval 2, open interval 4, and the radius of convergence is 1. So this is quite a long problem. I mean, maybe it wouldn't be so long if I wasn't writing the alternating series test and the p-series test, but it's definitely a full page and longer than the previous problems because you have to check the endpoints too. Okay, that's it. I'll see you at the next segment.